Okay, great. I'm still Micah, and I'm here to talk about anonymous group communication. This is joint work done with Dong Lin, who recently completed his PhD at UPenn, and his advisor and my former advisor, Boon Tao Liu. And I should thank Nikita for sending me Pokemon Go tweets during my last talk. I encourage you to continue to do that wherever you are. Okay. So the goal of this work is to support efficient group communication while hiding participants' network locations. It's slightly different than the type of group anonymity that we've seen before and is present in systems like dissent and verdict. So in other words, I want to support anonymous file sharing and streaming, for example, or anonymous audio and video conferencing. And so kind of a knee-jerk reaction to this is, well, we already know how to do this. It's use this system called Tor. And how might you do this in Tor? Well, these 6 users, say, want to do an anonymous video conference. And to facilitate that, they'll use Google Hangouts. So what they'll do is they'll connect to their guards and their middle and their exits, and they'll form Tor circuits to Google Hangouts. And this in theory should work, although it really works well if and only if Tor is really a drop-in replacement for TCP, and Tor isn't a drop-in replacement for TCP because of bandwidth constraints in the network. It's not essentially fast enough to do this at large scale. Hopefully it will be in the future, but today not so much. But in this work, we looked at, well, can we still use Tor, maybe with some modifications, leverage its existing user base and infrastructure to do group communication, but in a way that can be done more efficiently. And we started off by kind of looking at this very contrived picture and making some observation. And the first observation we made is that the same plain text, the same video conferencing information, if you will, is being relayed multiple times potentially over the same links. So there's some perhaps unnecessary, that's arguable, but perhaps some unnecessary redundancy there. And the second observation we made is that this external facilitator is for the most part kind of a fairly simple IRC or echo server. And I'm kind of skipping the Google Hangouts thing where you can add funny looking hats in people's heads. But for the most part, it takes communication from Alice and sends it to Bob, Charlie, and Dave. To kind of give you an overview of what we've done in MTor, the first thing we did is we removed the need for this external facilitator, and I'll explain how that's possible in a few minutes. And we also removed the use of exit relays. Now, Tor still has exit relays. We're still supporting unicast. We're not kind of changing, the 99.999% of the users who still want to use Tor unicast messaging. We're just introducing a multicast primitive for Tor that could be used by users who are so inclined. And in the place of what I'm calling the facilitator, we introduce multicast root, which is, as you might guess, going to be the root of our multicast tree. And finally, and perhaps most controversially, we take the links that have redundancy and we merge them together so that redundant information is only sent once. And it'll become apparent in a few minutes why that could be controversial. We're introducing multicast messaging semantics to Tor very kind of at a high level. This means that rather than sending to a particular IP, you send to a group identifier and people can join that group. And when you receive a message, you kind of subscribe to it. This is kind of like a pub subsystem, if you will. It preserves bandwidth by removing message duplication, and it also offers shorter round trip times because it eliminates this extra hop between the exit and the facilitator and then back. So there's shorter paths. And it also, and importantly, reduces the burden on exit relays, which are already overtaxed, by simply not using them. So the challenge here. Okay, so we don't want to open Pandora's box. We don't want to prevent flooding attacks, which is particularly dangerous for multicast systems, because if you can send one message and cause that message to be propagated 10,000 times, that's bad for denial of service. We have to kind of reinvent flow control because you don't have TCP-like or send-me-like end-to-end flow control, efficient churn handling and fast recovery, and also we should probably make sure we don't kill anonymity. In terms of security, we have some notion of authenticated messages. For flow control, I'm not really going to talk about this in this talk, but there's details in the paper. We do best effort routing, and we're introducing loss to Tor. You can now lose messages, which is a weird thing for TCP, but we manage it. For churn handling and recovery, we use a combination of heartbeat messages and a fairly fast multicast tree assembly algorithm. And I'll talk about anonymity that requires more space than I have here in a little bit. So what is the design of MTor? It begins with receiving a group descriptor. So if I want to join a group, I somehow get one of these descriptor documents. And this could be posted on a blog, you could fetch it over unicast Tor, you just somehow get one of these. And what this is it's basically a description of the multicast group. There's one per group. In this document, it describes some minimum bandwidth that's required. This is, again, because we're using multicast and loss becomes a factor, so we want to remove bottlenecks. So we impose a minimum bandwidth. And we use a blinded key generation scheme that Nick Matheson came up with a few years ago, and I think the context, I forget, of Tor hidden services. And briefly what this is you have a master key pair, a public key and a private key, and you can then, if you have the master public key and a nonce, you can generate a series of subordinate public keys, and correspondingly, if you have the secret key, master secret key, you can generate subordinate private keys such that those subordinate public keys and subordinate private keys match. And importantly, it limits the linkability between sessions. So if you don't have either of those two masters, you can't tell that these sessions are linked, and this is good for preventing linkability. And you can do this using Dan Bernstein's signatures, which Nick proved to be a correct implementation, so thank you. Confidential authenticity keys can be used to provide optional end-to-end guarantees. This is multicast, so we just you can have a layer of encryption on top of everything if you just want to if you want to make it so that no one outside of your group can look at the messages. In each epoch, in each time period, we divide time into time periods. Each client is going to use the master public key to generate a new public session key, and then compute a group identifier, which is a hash of the bandwidth, the session length, which I didn't talk about, in the subordinate public key. And a high-level picture here is that the group identifier is used to tie this public key with a particular group, and it essentially prevents forgery attacks or trying to substitute in a different private key. How is the multicast route selected? We use a consistent hashing-based mechanism. Basically, we take the relays, their fingerprints, and stick them on a ring. We also throw into their position is based on their fingerprint, the GID, and consensus. And we use all of those things to basically prevent a trivial attack and prevent an adversary from being able to game its position ahead of time on the ring. It doesn't know what the ring is going to look like. And the multicast route is simply the first relay past the GID in this consistent hashing space that is stable and fast and has sufficient bandwidth. And all of the clients can kind of agree on this, and we bootstrap towards existing consensus mechanism. The tree is formed by having client create circuits to its normal guard. So you use the normal guard. We're not changing how that works. A big difference is if the guard is already in the multicast tree, you stop. If not, you extend the circuit to a middle relay, again chosen using, for the most part, Tor's default relay selection strategy, except for the bandwidth weighting, except for the minimum bandwidth thing. And if it's in the multicast tree, you stop. Otherwise, you extend finally to the multicast route. And this is kind of a very typical design for multicast messaging systems. Messages are protected via TLS because it's Tor between relays, but we don't use layered encryption. That means that you can follow, the adversary can, if it has a sufficient view of the network, follow messages across Tor. And that's a weakness of our system. We don't particularly, we have kind of an argument in the paper why that's not necessarily a bad thing for multicast, or it may be unavoidable in certain cases. But if you've got a solution to that, that would be fantastic. We don't use layered encryption because we want to do message deduplication. If a message is going to be sent twice over this particular link, we only want it, or more than once, we only want to send it once because that saves bandwidth. And as I mentioned, this provides weaker security than Tor's current design. Cells are signed in MTor. They're signed using the subordinate secret key. And how the secret key, the master secret key is disseminated, allows a choice of open groups where the secret key is kind of public and anybody can get it and anybody can be a sender in the group, or you can have essentially an access control mechanism based on who has knowledge of this secret key. And we call that in this paper closed groups. And this provides some protection against flooding attacks because things have to be properly signed. So in terms of the performance, how well does this work? We implemented a bunch of dummified versions. These are applications that have traffic profiles similar to what the real versions would have of a single source streaming application. So, I'm sending to a group of people. Multi-source group data sharing, you're all kind of sending messages, maybe in kind of like a BitTorrent swarm type situation, and multiple source audio conferencing, so using Skype's codec. So everybody's kind of group audio conference. As our baseline, we considered the strawman solution of using regular Tor with some external facilitator that basically echoes things back and forth to the right people. We did both emulations in Shadow and simulations in Tor Path Simulator for various reasons, mostly to do with sanity checks, but also because of scalability reasons. Some results. Multicast Tor, unsurprisingly, saves Tor bandwidth. In other words, Tor has a finite amount of bandwidth. If you're going to kind of use audio conferencing using Google Hangouts versus MTor, we save Tor about up to a threefold, depending on the size of the group, savings in bandwidth that's required. So it scales nicely. The more clients you have, the less or the more bandwidth savings you get over the vanilla solution. Transmission time, so this is kind of from the client-centric view. These are cumulative distribution functions on the y-axis, and the x-axis is transmission time measured in seconds. And on the left graph, you have multi-source streaming. This is everybody's kind of sending each other big chunks of data. And you see that, well, our savings are significant. We have a 70% reduction in the median. And for audio conferencing, for vanilla Tor, we find that about 10% of the connections just won't work because the latency is so huge. And also really, if you're doing VoIP, anything above like 2 seconds is kind of useless anyway. It'll be too painful. So we do better, not just at the median, but kind of, I think the more important measure is the cutoff here at the top. What about anonymity? This was kind of hard for us to look at. It was kind of an interesting challenge because how you define anonymity for group communication is non-trivial, and it really depends on what you're trying to get out of your communication system. So if you consider traffic analysis in the, kind of my previous talk, or more generally, the adversary wins in that case if it can get in the client's ingress side and the egress side, and then it can correlate the two and say, okay, great, I can figure out where this client is coming from and where he's going, and I win. In the multicast scenario, well, there is no exit. Everything is really ingress traffic going into the network. All the traffic is going in through the guards and out through the guards. So there's multiple senders and receiver. So we say that two clients in the multicast group are linked if the adversary observes each of their guards' traffic. And this is kind of something hopefully not too arbitrary that we came up with. And we were also interested in membership identification or enumeration attacks. How easily is an adversary able to enumerate the members of a multicast group? We borrow the human understandable metrics from a paper that Aaron, Paul, Rob, and myself wrote with others a few years ago at CCS, that being the time to first compromise and the compromise rate. I'm going to skip the compromise rate for now. The details are in the paper. But in our experimental setup, the adversary had a ton of bandwidth, as much as at the time that the study was done, the largest Tor family, and the adversary is going to use that bandwidth to operate guard relays to attract as much traffic as possible. And we simulated the adversary and MTor using a modified version of Torps. So what we find is that we don't do, it's kind of mixed results. The membership identification really depends on how lucky the client is in selecting its guard. Now, importantly, this was done before Tor changed how it does its default guard selection strategy. So I think today the results would actually be significantly better and more secure than this. Really, what this is a measure of is how lucky are you in selecting a good guard. If you select a bad guard, then that guard can figure out that you're in a multicast group. If you choose a good guard, then you're okay. Am I out of time? Okay, I'm really out of time. Okay, so in summary, MTor enables low latency anonymous group communication. It scales gracefully to the size of the multicast group. And using data from the live Tor network, we show that we have significantly improved performance, and we can make this practical for real-time applications. Thanks.